Select the major product of the following series of reactions. So if we look at our given starting material, we can see that it contains an ester and an aldehyde. And let's take a quick look at what we're reacting this with. So in step one, we're using a diol, so it's a little molecule with two alcohols, and a dry acid catalyst. And in step two, we are adding methyl magnesium bromide, or a Grignard reagent. So this is a Grignard reaction. So noticing this Grignard, I know that a Grignard could react with an aldehyde and it could react with an ester. It's more likely to react with it's going to react with both actually if you have enough of it, which it says we have excess. It would react first with the aldehyde, but definitely it would continue reacting with that ester and would be difficult to control. So if we look at that first step, right, hopefully we can recognize that these are conditions to protect either an aldehyde or a ketone as an acetal. So here is the general reaction to form an acetal. So you've got a carbonyl, two equivalents of alcohol, and some sort of dry acid. So HCl gas is a good one. Dry is important, meaning excluding water. And that would help you to form an acetal. So this is what an acetal looks like. So something like this, okay? So when you have a diol, when your two alcohols are attached together, you form a cyclic acetal. So here's what we have in this case. We have two equivalents of this ethylene glycol would be the common name for it. So we can see that this is 4 atoms. So this is going to give you the same structure. It's just that your two R groups are attached together. So when you have this and your acid catalyst, you want to recognize that the acetal carbon is going to be part of the cyclic acetal that you form. So that would be 1 atom, and then 2, 3, 4, 5. It's going to be a 5-membered ring. So this is what your cyclic acetal is going to look like. So this is a cyclic acetal. And so these are often used as protecting groups, and that's what's going on in this first step. So if we take our aldehyde, which is more reactive than the ester, right? So notice we said this is only to protect aldehydes and ketones. This will not protect an ester. So what you will do after that first step is you will protect the aldehyde as the acetal. So you will have this cyclic acetal. And you can check your number of carbon atoms to make sure. So I'm just going to number from carbonyl to carbonyl so we can kind of see what came from where in this structure. All right, and so what this does is it preserves the oxidation state of this carbon that I've numbered as number 5. We can see that because here this carbon has 2 bonds to oxygen, 1 bond to hydrogen, 1 bond to carbon. It still has 2 bonds to oxygen, 1 bond to hydrogen, 1 bond to carbon. So the oxidation state is the same. But by removing the pi bond, we make this carbon 5 no longer electrophilic. So the Grignard reagent cannot attack carbon 5 because you don't have that pi bond that can break. So all it's going to do is react with your ester. Right? And so your Grignard, the first equivalent then, can add to the ester. And this should be a familiar reaction. So O minus now, we can show the new bond to the methyl group that was added. So this is a tetrahedral intermediate. Right, and so we still have that. If we want to keep track of our carbons, I'm just going to use the original numbers. Anything that we've added, I'm not going to number. That doesn't mean it's not there. It's clearly still there. It's bound to this carbon 1. All right, and so what happens when you have a tetrahedral intermediate is if you have a leaving group like you do with an ester, this can collapse and your leaving group can leave. And so that's going to happen, giving you a ketone at this end. So you've got that new CH3 group that you've added, the carbonyl. And this was our original carbon 1. So 1, 2, 3, 4, 5. And here's our acetal carbon. And I better make sure that's a hydrogen. And now they have a ketone, and this ketone, of course, can react with the Grignard as well. It's actually more reactive than that ester, so we're not going to be able to stop this. It's going to add. So we will have this add to the carbonyl. And so now we will have this, another tetrahedral intermediate. So we've added 2 methyl groups to it. And so this was our original carbon 1, right? So it's 1, 2, 3, 4, 5. So here's our acetal. And so that's where it's going to stay until you add aqueous acid, right? And so once you add aqueous acid to this, you will end up with B. So I'm going to go ahead and redraw this below B so you can see what's happening. So we have that alkoxide. This was our original carbon 1. And so when you add your aqueous acid, you're going to protonate here. So I can draw that mechanism. That one's nice and fast. And so we're going to protonate that alcohol. And you're going to, so protonate the alcohol, or alkoxide, I should say, to form the alcohol. And you will hydrolyze that acetal. So acetal hydrolysis means you are cleaving that off. You're going to restore this to be the carbonyl, and this will go back to being the diol.